All right, welcome. In our last video, we looked at maximizing utility in a deterministic environment if we have explored the whole environment, if we understand or we know the model of the environment. However, we stated in that video that it's common that we don't know the whole environment, we haven't explored the environment. So in this video, I want to look at strategies for exploring in deterministic environments so that we can learn the model and then apply our utility maximization algorithm that we looked at in the last video. So again, we're going to start out in a similar position as we were considering last video, which is we're a robot that is trying to learn its environment. Maybe you're a human, maybe you're a newly born human, you're trying to learn about the world, your environment, and at this point it is unknown. You are sort of at the blank slate stage, you don't know anything about your environment. It's observable and you have the tools to observe it, and you can take actions in that world. For the moment, we're going to assume we're in a deterministic world. That just makes things a little bit easier on us to get started. And remember, deterministic means that for any action that we carry out, there's only going to be one effect, one output, or one state that we're going to arrive at. There's not going to be any randomness or non-determinism involved where we're uncertain about what the outcome is going to be. Now, when I say that at the beginning where this robot is right now, the robot is uncertain about all of its actions. It's never carried out any action and it doesn't know what any of those resultant states are. But should it try an action and explore that state, that action will be a deterministic action, meaning there will only be one outcome. How does that make it easier for us? Well, it means that we only need one observation of an action from a particular state to learn that part of the transition function and reward function. We don't have to sample that action more than once. So I've already sort of hinted at this. The goal here is to learn the model, and remember the model is the transition function and the reward function together. So transition function telling us which states we move into as a result of our action, and then the reward function telling us what payout did we get for arriving at that state, if any. And we know that if we have the whole model computed, then we can use that to determine what the optimal policy is. Remember, a policy is just a strategy, which actions I should take in which states in order to maximize my utility. That's what the optimal policy does. You can have a different policy that doesn't necessarily optimize your utility, but the optimal policy is intended to give you the maximum utility. So our goal is to try and explore the environment and try and find actions or states that are, find the goal state, and then use that to hopefully compute our optimal policy. And so again, we're just doing this in a process of trial and error where we will try an action and see what happens. So maybe our robot tried to move north first or up and it fell in the pit and it got a, oh, ouch, that's a bad outcome. So we'll remember that, but we remember the reward from that pit, and we also remember the outcome of taking, where the pit was basically relative to the square that we started in. And then maybe, after that failure, maybe we try another couple moves. Maybe we tried moving to the right and we find out there was a wall there, so we ended up in the same state. The same thing when we moved to the south. And we can continue that process to explore our environment. And if we're lucky, maybe we follow the path that we discussed in our last video, and we find the goal state. After a while, we've explored the environment enough that we traverse these states and end up in the pot of gold. When we get here, it's now possible for us to compute the value function. We can compute it at any time, but until we reach a goal state, we don't have any sort of positive input into that computation. So all our states are either going to be zero if you're working with a zero reward on normal non-goal states, or as I presented in the previous video and as I'm doing in these calculations here, I'm applying a small penalty, a -5 penalty to all of the states to try and encourage shorter pathways in this environment instead of longer ones. So in this case, we're applying the penalty when we're computing the value function back. And as you can see here, some of the value functions that we've actually computed are correct. Correct meaning we computed these last day in the last video, and we saw that this was an 85, this was 7. These ones are correct up to this point here, but this 30 and this 22 and this 15 are not the correct value function for those squares. They're only the correct value function relative to the observed squares, the squares that we've actually had a chance to traverse. And there's one square right here that there's a shorter path to the gold if we cut through here past the pit. And if we recorded that one, if we observed it and maybe traversed that path, we could update the value function and compute the correct value function or the actual utilities for all these states. So we sometimes call this a partially observed state of the environment, where we've observed enough to find a goal state or maybe a couple goal states, and we've calculated the value function relative to the observed states. That gives us a strategy of a path that we might want to follow, and ultimately it puts us into a exploration versus exploitation question or trade-off. In this position, as the robot, we can now decide, should we follow the path that we found that has a particular utility. From our starting state, its utility is 15 according to our discounted rewards calculation here. That's still positive, so that might be good enough. So do we stick with this, or do we decide maybe we should explore some other paths to see if there's a better path that we can find through the environment? Of course, knowing that there is one in this simple state that we create, in the simple environment that we've created. So this is a trade-off that we face a lot when we're exploring. And there are a couple different ways that we can respond to the trade-off. So for instance, if we know that our environment is small, like in this case, we started with a very small environment, we might just say, well, I know my environment is small, I'll just deliberately explore the whole thing. Because once it's completely explored in a deterministic environment, at least, we have all the information we need, we can compute the optimal policy, and then no more exploration is required. So this is a good strategy in small finite environments, or finite environments that are large enough that a complete exploration is not feasible, like right off the bat. You can still have this deliberate exploration strategy if you know your environment is finite, and in the lifetime of your robot you will have enough time to explore the whole thing. Then it's probably valuable to go out and try and explore as much of the environment as possible while exploiting good paths in for whatever particular task it is that your robot is trying to learn. So this is one strategy, but then what happens if your environment, like I said, is really big or is infinite? It does not have a finite number of states, so complete evaluation or complete exploration is impossible. So in these ones, we need to come up with a different kind of strategy. And one of the strategies that is popular is called the epsilon greedy strategy. The epsilon greedy strategy basically just uses a parameter, we call it epsilon, that determines how much we explore. So say we have a choice on any particular action, we're in a state and we can decide, do I want to explore in this particular state, or do I want to follow the optimal policy that's already been computed for me? And we use epsilon, we kind of flip a coin, and if with epsilon chance, we will do the exploration option. And with 1 minus epsilon, whatever's left over, we will just follow the optimal policy. And then there are a few different variants of how this strategy is applied when exploring. And these are just a few that I've listed here, but there are more than just these ones. So the first one is just sort of naively. So we just have some parameter, and maybe it's 25%. So 25% of the time we explore, and 75% of the time we exploit. Now that's, it's naive, because typically in any environment, your desire to explore is going to be dependent on other variables. You're not just going to have a flat desire, well, I just think a quarter of the time I should be exploring. In parts of the environment that you've already explored before, for instance, you probably don't want to explore at all. You already explored that. Just exploit the optimal policy. And then in other parts of the environment, you might want to explore a lot. So there are a couple ways to address this sort of contextual need for exploration. One way is also temporal. So the first one here, decaying, is recognizing that early on, our robot as depicted right now hasn't explored anything. It should be exploring a lot. It wants to figure out what the environment is like right now. But after you've got some of that information over time, we assume you're going to learn more about your environment. You should probably explore less and less. So one strategy is to decay epsilon as you go. So if you were just going to use a naive strategy, as we were talking about, 25% is probably not a good chance. That's over exploration. So usually if you're just doing naive, no decaying, you would probably set your epsilon pretty low, 5%, 1%, something small enough that makes sure that most of the time you're exploiting, so that once you do learn a good strategy, you exploit it. But in the decaying strategy, you will usually start your epsilon quite high, maybe at 100%. And then over time, you will decay it so that hopefully, in the same scenario, in the future, once you've learned some good strategies, it's decayed down to a small value close to zero, and you are exploiting most of the time. Another way to make this work is variable. So I've already mentioned that maybe your desire to explore is going to depend on context or variables in the environment. For instance, it might depend on how many times you've explored already in this region. So for instance, our current robot here is in a state where it has 4 actions and it has explored 0 of them. So in that environment, you're kind of forced to explode. Hopefully you don't explode. You're forced to explore because you don't know what the optimal policy is. So in this case, we might say your epsilon should be 100. But then maybe if you've explored one of those pathways, you might say, okay, now that I've explored 25% of my options, maybe I should only have my epsilon set to, say, 75%. And of course, there's different strategies you could take here, but this one's kind of an obvious linear one. Then when I get down to, now that I've observed maybe 2 of them, I will switch it down to 50%. And then once I've observed 3 of them, I'll go down to 25%, and then of course once I'm down to 100%, I should just exploit every time. So that strategy is, we might call that a variable epsilon strategy, where each state now maybe has an epsilon, and the robot determines whether it's going to explore or exploit from that state, depending on how much it is explored before. So these are a couple different variants of the epsilon greedy strategy, which, as I mentioned, is a very common strategy for exploration. So before we take a look at that, I do want to just take one more or do one more sort of thought experiment here, which is, what do we do when we decide we want to explore? So the obvious kind of answer is, well, just pick one randomly and uniformly. And this is still a strategy that's used a lot, even though there are some theorems related to what's called random walks that tell us that if you just make random steps, you're not likely to get very far. So for instance, consider this simple experiment. Say you're on a sidewalk, or I picked a sidewalk because there's sort of like those discrete tiles on the sidewalk. So maybe you're standing on one of those discrete tiles like our robot is right now, and you've got a coin. You flip a coin in your pocket, and when it comes up heads, you go 1 tile to the left, and when it comes up right, you go 1 tile to the right. So this is what we would call a random walk on a one-dimensional grid. So just for a moment, think to yourself, let's say you flip the coin 100 times. Think to yourself, how far do you think you will move from your original grid cell when you do this little experiment? And so think about that for a second. And think about, well, what would the maximum distance away from my original cell could I be? What is the minimum distance away from my original cell could I be? And then if you can kind of conceptualize it, what would be the average or expected cell, the cell that you would expect to be in after flipping the coin 100 times or 1,000 times or whatever it might be? And while you're thinking about that, let's take a moment to go take a look at an implementation of that. All right, here I've got just a simple random walker simulation where I've just implemented that simple experiment that I mentioned. I've got a agent that will be in a cell, and it will just flip a coin, or has a 50% chance of either moving to the left or moving to the right, or that's what I'm calling a one-dimensional walker. So let's see what happens. So this is my one-dimensional walker, and it's walking back and forth. And I've got it on set on really fast right now. It finally escaped off to the right, but luckily we've got some stats up here in the top that we can follow. We can see that it is gone for about 10,000 steps, and it has explored 268 cells so far. So it's actually doing really well. This is uncharacteristically good actually for a random walker, which is after about 20,000 steps, we've already got to 400 cells. I said this is uncharacteristically good. Let's start one over and try another one and see if we can get one that's maybe a little bit more characteristic. So here we've got one that's also doing very well. It's scooting off to the left. Why do I say this is uncharacteristically good? If you're going to keep going to the left, that means you're getting a real lucky streak. Oh, see, here we go. Our agents decided to come all the way back to the beginning. It means you've had to get a really lucky streak of heads. That's unlikely. So for you to explore that much really early on means you got a really lucky set of coin flips. But now we've got an agent that's kind of doing what I was expecting it would do. It's really just hovering around where it started out. And you can see I'm registering how many times we've stepped on each one of these cells. So those white cells there mean that those cells have been stepped on over 255 times by our agent. So now we can see, again, still kind of uncharacteristically good, but at around 30,000 steps has explored only 300 squares. Let's do one more and see if we can see. So again, I kind of want one that doesn't escape our view, and maybe we can watch it just kind of go back and forth here, and it will slowly, turn all these cells white. Basically, what are we seeing? We're seeing it exploring the same cells over and over again, ones that it's already seen. So there's got to be a better exploration strategy than just randomly moving back and forth. That's sort of the takeaway that I want to get from here. Now, I've done this in one dimension because it's actually the worst it can possibly be in one dimension. Okay, you only have left and right, and you kind of hover back and forth around that middle point. Let's try it with two-dimensional. So this is a two-dimensional random walker. Okay, that one's already kind of escaped. Now with two dimensions, you have what we call 2 degrees of freedom. Let's do another one. We'll just keep adding them in here. So this means now both of my random walkers are going. In fact, why don't we start off a couple more? Boop, 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 boop. They're all walking around. One thing we will see with the 2D ones, just like the 1D ones, they tend to stick around in this middle area. Okay, so we've got 5 that have escaped, and 2 or 3 here that are still trapped inside here. But they are doing a little bit better of exploring. You can see that after 80,000 steps. So now that I've got a bunch of different walkers here, I'm not just measuring ticks, but how many steps they've actually taken. So with 100,000, we've explored about 20,000 squares. So that's not as bad a ratio as we were seeing with the 1D walker. But still, there's lots of repeating. You can see that at any one local position, they tend to just jitter around in that local area a lot. And you might think, okay, well, what kind of organisms or animals might we look to for inspiration about this? And we see, for instance, there's lots of animals that need to forage for food. I have some expertise with insects. So one particular animal that forages for food that I know about is an ant. So an ant will leave its colony and it will go out and look for a food source and either bring that source back or bring it back and report to the other ants, hey, there's a big food source over there. Let's work together and bring the food back to the colony. Now, when an ant decides to explore its environment, it doesn't look like this. It doesn't just jitter back and forth, jitter, 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 and kind of, look like it's having a little seizure. Of course not. That's not very efficient in exploring the environment for food. You shouldn't be exploring parts of the environment that have already been explored. Now, ants have a couple different strategies for how they can explore the environment, but one of the strategies that we have is there's a better kind of random walk than just randomly picking your direction every time. And this kind of random walk is sometimes called the drunken sailor walk. So the idea of a drunken sailor walk is that the drunken sailor is trying to walk somewhere, maybe back to his ship, and is drunk though, and maybe gets distracted by things and wanders off the path. But for the most part, we like to think that the sailor is able to find their way back to the ship, in which case the ultimate path that the sailor takes is it gets you to the destination, but it's ultimately kind of a windy exploratory path. So we sometimes make our random walkers try and be inspired by the drunken sailor, and we sometimes call these drunken sailor walks. And in my little simulation here, I've created a drunken sailor as well, and I've made a very simple drunken sailor. There's different ways you can make your drunken sailor walks. The way I've made it on this simple grid environment, my current random walker just randomly picks a move, up, left, right, or down. My drunken one will randomly pick a move, except for moving back to the cell that it just came from. So the only rule that it's going to add is don't backtrack. And it's only going to remember the last cell. So it's not going to remember 7 cells or 12 cells and not try and run back into its path. It will only remember the last cell. Let's see that one. Well, this one actually usually, this one stuck around longer than I expected. They usually kind of escape pretty quick. The one thing we can see is when we're looking at the number of steps it has taken relative to the number of explored cells, they tend to be much closer together. You tend to explore a lot more cells. So wherever that drunken walker is now has exited, has explored almost 7,000 cells in about 17,000 ticks. Let's add another one. Okay, again, this one stuck around for a while. So again, it is possible for you to backtrack on your own path, but then you might have to get lucky and go right? Like to get back to the same square, you can't just immediately go left then right and back at the same square. You have to keep turning around and do sort of 4 squares before you can get back. That alone allows them to explore, as I mentioned, a great deal more. And in my simulations in the past, I've actually implemented some ants, and we've had an exploration strategy, and we did something very similar to that. No backtracking, but what we did is we said, also we increased the chance of going forward. So if you think about it, if you know what your last cell is, then you know what direction you were moving. Were you moving up? Were you moving left? Were you moving right? Were you moving down? So all we had was that when you were moving forward, when you moved in a cell, if you're in your drunken sailor exploration strategy, you will, with 80% chance, move forward, and with 10% chance, move to the left or the right, or something like that. I can't remember the exact percent variables. It might have been slightly different, 50% chance forward and 25, or something similar to that. But we just altered that probability spectrum to try and just weight us into moving forward, and that also allowed our random walkers to explore a little bit more naturally. And what we were aiming for in that case was to try and make something similar to ants walking around, which tend to follow what we might call this drunken sailor walk. So as I mentioned here, for this reason, when you are designing, well, how do we explore, you want to be a little bit more selective than just random. Random is a very obvious and easy way to implement, but it is sometimes not super good at exploring your environment. So the last thing I want to look at here is in our last video, we looked at doing value iteration on a deterministic world where we have the known model. And what we can now do is kind of interleave these two ideas and strategies. We are commonly not in worlds where we have a whole known model. If we do, then we apply one of those other offline strategies. If we're in a world that we don't know the whole, we haven't observed the whole environment, then we are commonly in states of partial observation. And in those states, we can compute the value function, but the value function might not be accurate for the actual utilities of those states. And that's why we get forced into that exploration exploitation trade-off. Now, what that means is we can kind of take that exploration strategy, maybe that epsilon greedy strategy, and then we decide when we're exploiting to update the value function so that we have an updated and accurate version of the value function, as accurate as we can get, to predict the optimal policy, and then again follow the actions to arrive hopefully at a goal state. So I'm going to start with our very simple environment here, and I'm also starting out with the fog of war on, sort of indicating which cells we have explored, our agent has already explored. You can also see I've got the value function initialized to 0 for my value iteration algorithm. And what we're going to do is, as we go explore out, my first agent is going to be very naive. My first agent is going to do a sort of random walk, and it's going to only update the value of a cell when it explores that cell. So only in the moment when it explores that cell. So we have the opportunity to explore all the observed, but in this particular example, it will not. So let's take a look at this first agent. Now I've got it set on kind of slow, so it accidentally fell in the pit. And it's sort of moving around here. And again, I mentioned it's on a random walk. So you can see it's kind of it's getting stuck going back and forth like we saw, and it keeps updating these cells. Now, this particular robot is doing an epsilon greedy strategy, but it is an epsilon decay strategy. So in this case, it's got an epsilon, at the moment, epsilon is 1, and only after 100 ticks is it going to decay it. So right now it is just purely random walking. And this is only its second run. Its first run, it fell in the pit right away. Its second run here, oh, it finally found the goal state. So you can see it's updated that one. Okay, it fell in the pit again. Oh, geez. It's still on full random walk, right? And so with full random walk, it's been running into that wall. So again, just doing random walks, and fell into the pit again. I'm hoping it can get back up to that square and maybe update its utility. We've only done 67 ticks here. Now that we've observed it, let's try and speed it up a little bit and watch another random walker. As we can see, it takes a little bit of time for the random walker to explore and find the goal state. Oh, there, it's found one. Oh, it's got itself up around the corner. Will it make its way all the way there? It's getting stuck going back and forth. We've now finally decayed on this example, and so now with 10% chance, we're going to just follow the optimal policy. We keep jumping in that pit, unfortunately, but now we've almost computed the value function for every single cell. And now we have computed the value function for every single cell. So the only reason we're falling in the pits now is because we keep following an exploration strategy that we probably shouldn't. So maybe we see here, okay, so I like the speed we're on. Maybe I'm going to speed us up just a little bit more. But let's be a reinforcement learning kind of designer and decide, okay, what should we do here? We're not learning fast enough. We could either turn up our decay, or turn down, I guess, make it 75% or something like that. Or we could change how many ticks it is for us to decay. I think I'm just going to change it to 10. I'm just guessing a new parameter. This is kind of how we do it. We can see our robot now is still jumping in that pit a lot, although sometimes if it gets lucky, it will follow its policy and get into the gold. It's not doing the back and forth quite as much anymore, but because its exploration strategy is its epsilon is still at 65%, it's wasting a lot of time jumping in that pit. We're at negative 5,400. Okay, so let's try a new agent. So I've sped it up a little bit. Again, at first we have to be kind of random and get lucky. Notice we're already down to 43. Oh, look at this. So we've got the value function for these 5 states. We haven't explored the other outside enough to find the other path. We keep jumping in there when we're exploring by accident, but notice our epsilon is all the way down to 10% now, And we are probably not going to explore that other path now unless we get really lucky or unlucky, depending on how you consider it. And we've learned this path and we've exploited it. So this one's actually turned out to be pretty good. I want to run it again and see. Okay, lots of time jumping in the pit. We finally found it. We were going around the outside. Okay, but we've now found it, and we're at about 43%. Are we going to jump in that pit again? Oh, one more time, it looks like, or two more times maybe. Oh, a couple more times. And we've got to positive reward. Oh, we've jumped one more time. We're finally now exploiting enough. We're in the positive reward zone, and our epsilon is now down to 7%. Looks like we're going to be, oh, we still, unlucky, really unlucky. We explored and jumped in that pit a few more times. Okay. And again here, in this small environment, this simple random walk kind of worked for us, and we found some settings that made it work. It's exploiting it, found the right thing. So I keep saying this is sort of a simple environment. Let's look at a slightly trickier environment now. This is a maze environment. Now let's just take a second to solve this one ourselves. We go around here, something like this. Okay, it's not too bad. Okay, this whole other part of the maze, you know, if you don't go this way, you can get lost in a whole other part. This is not a very bad maze, but let's try. Okay, I've got us on 0.1. Let's leave us on the same settings here. Actually, 10 is not good. Let's put us on back up to 100 here. And let's start our agent. Now remember, we're on random walk. And even though this is a maze that's got some lefts and rights and so on, it's kind of like the one-dimensional random walker, because most of the time the agent is in a state where it is like right now. It has two options of where to move, left or right. It can move, you know, up, it can move in one direction or the other direction, and it just gets stuck doing a random walk. So unfortunately, unless it gets really lucky, and we can watch this one for a while, it's not going to get there. So I want to, let's speed it up. Let's go a little bit faster. Bzzz, okay. Can you make your way to the end there, little robot? I think this is the fastest. Oh, okay, we got there once. Now the problem again is I've also got a very naive update strategy on here, meaning that we only update the value function every time we enter that state. So you'll notice it takes it every time it has to follow this path down to the pot, it gets one more cell calculated in its value function. So it's going to take a while for it to, you know, propagate that calculation all the way back to the beginning. Luckily, the path to the output here is actually very one-dimensional. So once it's found it, notice it's at an exploitation of 5% now. It's going to learn those other ones. It might random walk over there a little bit until it's propagated that back. And now with epsilon of 2, we should expect it to just be gobbling up that pot of gold every single time. Okay, so not that bad, I guess. How many ticks? We got 3,000 ticks. Maybe let's try it one more time. Actually, let's do a new maze. Let's see. This one's not bad. Let's try this one out too. Doesn't have too many turns that it can get caught in. Uh-oh. It found itself into a part of the maze where it can get caught for a while without... And now look, it's got nothing. Oh, it found its way out. That's lucky. Okay. But it has to get lucky every time until... Okay, there we got some. So it can propagate that value back. And here, okay, there you go. All right, it's looked like it's doing pretty well. It doesn't look like it's going to get stuck in that other part anymore because it's gone and explored and it realized. And remember, I can actually show here what it's thinking. For every cell, it's trying to move to the cell with the maximum utility or maximum calculated utility or value function. And so it's actually got this strategy now. Again, its epsilon's all the way down to 3%. So 97 or 98% of the time, it's just going to follow this arrow, the arrow that's pointing to the cell with the highest utility around it. And that means even if we grabbed our little robot and we plopped it down somewhere else in the environment, at least somewhere where it's calculated the value function, it should be able to find its way to the goal state. Okay, so I mentioned this is a little bit harder for it to compute. At least we've got turned it on really fast and we've got lucky a couple times. Maybe I'll do another maze like this. I'm going to turn off the solution for a second. Okay, this one looks like it's a little bit harder to learn because we have to scoop all the way around here, all the way back around. It's got a really long path. See, it's managed to get it. So we could let this one go, but what I'm going to do is I'm going to show a slightly different strategy. So I'm going to maybe turn us back on a little bit slower. And I'm going to turn on what I have called Explorer mode. So Explorer mode means that if there is an unexplored action, I will explore that action instead of backtracking. So you'll notice the first pass through got us to the end almost right away. It kind of just walked right there. It got lucky and it didn't pick any of the paths it shouldn't. But then once it's found that path, it is now stuck in random walk again. So this is a good technique, but not necessarily in our naive update schedule. So we can update our value function every time we enter one of the states. That's what we're currently doing. But we can also update all of the observed elements. So in this case, it's called update explored, which means that every time it gets a chance to, it will update all of the explored ones. So not these ones that are in the fog of war still, but all the ones that it has explored. So let's try a new one. So you can see now all of the value functions are updating as we go, okay? Because every time we're calling update on all of them, we're just doing value iteration, but we're doing one iteration of the value iteration function. We could run the whole value iteration function, okay? So in this case, we've done it. Now, here's the curious thing about this, is it's actually computed the value function all the way back, but because our path was so long in this environment, that the decay function actually causes it to turn negative after a while because of those -5s, okay? Now we're stuck in that same problem we had with our small environment, which is our agent has actually learned the environment. It only took it one pass, and then it went and well, now it went and explored back here, so it's got some more information. It didn't need to, but why did it explore back there? Because it's on epsilon. It was still around 65%. So now that we've got a better learning strategy and learning schedule where we've got Explorer turned on and we've got Update Explored turned on, let's fire off our agent again. Well, it took a wrong turn there, but it was doing pretty good. And now we've got Update Explored. Look at it updating them all, propagating back. We're already at epsilon 15. So, well, I guess we chose to explore that. We do have Explorer turned on, so we are exploring. And at this point, it's computed the value function. Its epsilon is at 5%. And it's only computed 2 passes through the maze so far. And it's already optimized itself, even on this very long maze. So again, this is maybe more accurate of how we might use reinforcement learning in a maze-like structure like this. Now my maze also, this is a maze that only has one solution. It's kind of a traditional maze, but I can go ahead and delete some walls and add some pits in. See what happens here. Of course, my random maze generation isn't super intelligent yet. It put a pit right next to there, so let's try a new one. I need to check to make sure there's a way to get through. I think this one does have a path. So now let's add an agent in and see what happens. Again, we're still on Explorer. We're still on Update Explored. Okay, it's looking for any path. There's more than one path now that we've deleted walls. So that makes it actually a little bit trickier because it gives it more options. The other one kind of got forced to find the one path. This one hasn't found the path yet. It's found a few pits, all the pits actually, but now it has found it. And look at how it's updated the function for every single square that is, well, now it's observed every single square. And let's turn the show solution on. This means it's got lots of different paths, and those paths, so let's see if we can follow the path it wants us to take. So this is interesting. It's down, 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 down. The arrow's pointing right, but these are both 840s, so our robot is breaking ties different than our arrow. Our arrow's going right. Our robot chooses to go down. And then it keeps following this path. This looks right. Yeah, that seems accurate. But let's follow this other path. Where does it go? Up. Okay. So that other path, the interesting thing about the other path, oh, now it's taking the other path. The interesting thing about that other path, so maybe it is randomly choosing between those ones, or maybe it's updated its value function. There's decimal points that are not being displayed, so maybe it had a slightly different decimal point there. But the other path that has the same weight must have the same distance or same number of cells to travel, or else its value function would be updated one less. You'll notice there's sort of a continuum. There's the 8995s, and then there's the 8090s, and that's because these are 1 away, and those are 2 away, and then there's 3 away, and then there's 4 away. So if you are 17 away, you're going to have the same square as every other one that is 17 away. So this one that's 840 is the same number of squares away as this one that's 840. That's how the value function works. Same as this one that's 840 actually as well. This one has this path, and this one has this path, so they go different ways to get to the goal state. And again, we could plop you down, now that this robot has explored the entire environment, we could plop you down in any square and it should find its way. You notice that when it randomly picks one of these other paths here, it sometimes goes and takes this path. It takes the north path, and that's the just as equal weighted, equal utility from the robot's perspective. And now that I've been talking for a while on these settings, the robot is exploring not at all. Its epsilon is down to 0, or at least, again, there's a decimal point there. Maybe it's 0.0000001. It's got a very, very small chance, but for the small path that it's taking, the chance that it explores even once in that time is maybe really small. And over here, when it's taking that other path, I'm now convinced that I'm pretty sure it's because it's just breaking ties over here. It sees 2 and it doesn't know which one to do, so it just randomly picks one. And it mostly takes this bottom path, because you saw it just did this one. It just sort of jerked right here. There's more than one path for the bottom path, but there's only one lucky path that goes all the way to the right. And that's if you take those two. So there's 1, 2, 2 paths that go to the bottom, and 1 path that goes to the top. So it's 1/3 of the time it should be going up to the top, and 2/3 of the time it should end up going to the bottom. So that's interesting, curious outcome that we got from this interesting maze we got, where we ended up deleting some of the walls that might have been there to cause this interesting part of the path. All right, there's one last environment that I want to show you, which is my ice bridge. Maybe I'll turn my solution off for the moment. So I call this an ice bridge because in our next video, we're going to add slippiness to our environment. So when I try to move north, I don't always necessarily move north. I might slip to the left or to the right. And for that reason, this environment is very perilous, because this environment has pits all around on the side, and you have a bridge over the pits that lead to the goal, and we start out at the top. So let's start an agent in this environment. Again, this agent is on Explorer. This agent is on Update Explored, but it hasn't found a goal state yet. It's found a lot of pits so far. It's exploring that bridge state, saying, hey, I wonder, but unfortunately we can see the pits, it can't. It's now avoiding the pits that it's determined are not good, because its epsilon strategy has already decayed to 9%, and now that it's found some of those goal states, it is going to exploit its path to those goal states. Okay, so it found another one only because it moved its way down, and then its explorer kicked in and told it, hey, explore this new step that we haven't looked at before. But it's probably going to exploit these 3 golds as much as it can, unless it for some reason ends up in one of those other columns. You'll notice we're plopping the agent down in one of those top squares, but it's a different one every time, or it's a random one every time, so that it has to follow different paths each time, meaning that it has to optimize all the cells in its explored environment. So this is, again, using the value iteration algorithm in deterministic environments. And this is sort of an older school way of doing some reinforcement learning, but it's great for smaller environments or environments that are safe to explore in their entirety, like we've done in these ones. But in our next video, I want to add in another dimension to our environments, which is stochasticity or randomness or probability or a probability of error or a probabilistic reward function or a probabilistic state function. And one way we can do that in this environment is I'm going to click my ICY on, turn my ICY bridge on. And now what happens is the agent has a 10% chance of slipping. So even if it chooses to move down, it will have a chance of slipping to the left or the right. And what we can see as a result of that is that for the value function that we've updated here, the value function on the cells closest to the edge is actually less than the ones in the middle. And we'll see why that is in our next video. Well, the obvious reason is we don't want to slip into the pits. Okay, so we'll see why that is when we start looking at probabilistic environments. So thanks a lot for watching this video, and we'll see you again in that next video.